So we have this new thing we can do with variable functions of two variables. We can do double integrals with them. Because double integrals are built on top of limits and sums, right? However, whichever version of a double integral you use, and assuming the function is continuous, these are all equal to each other by Fubini's theorem. But because all of these are built on limits and sums have some very nice properties that they pass on to double integrals. All of these properties we're already familiar with for single integrals, but it is good to sort of understand that these properties are true for double integrals and why they are true for double integrals, right? The properties I'm talking about are these sort of basic facts about integrals. These are such basic facts that maybe you don't even think about these at all. You just sort of use them without thinking about them because they're sort of so fundamental to how we work with integrals. So one is, if your integrand is a sum, well, if you think about the sums and the limits that make a double integral, sigmas appear to distribute over sums, and limits appear to distribute over sums, and so double integrals distribute over sums. In other words, there's a sum rule for integrals. Similarly, if you have a sum with a constant inside, right, you can factor that constant outside the sum, but if you have a limit, you can then slide the constant outside the limit. The double integral is built out of sums and limits, and so if you have a constant multiple in an double integral, you can slide it outside of the double integral. We're familiar with that from single variable integrals. Okay, another property of double integrals that geometrically is very obvious, and that also has a corresponding fact about single integrals, is that if you want to integrate over a region that is built out of two smaller regions, right, so this notation here is S union T. Right? Union just means S together with T. So if we have some rectangle over here, S, and some rectangle over here, T, as long as these rectangles don't overlap, then the integral over S and the integral over T, if you add them together, you get the same thing as the integral over both S and T. I mean, that is so geometrically clear that I don't think that there's too much to say about it. So if you can split your region of integration up into pieces, as long as those pieces don't overlap, then you can integrate over them separately. Incidentally, the reason that they can't overlap is if your regions did overlap like this, then calculating the integral over the two regions separately, it would double count this overlap region. So that's why we have to insist that they not overlap. Okay. A couple other things. These are exactly the same sort of facts that you no doubt learned about when you studied single variable integrals. So if one function f is always bigger than another function, then the integral of f has to be larger than the integral of g integrals over some certain region, right? This is just because if your graph of f is above your graph of g, right? If f is up here, g is down here, and the xy plane is down here, right? The volume over f is just bigger than the volume over g because it contains the volume over g. Okay. Of course, I said volume. Really, we should be talking about signed volume, but the same argument works for signed volume. One special case of this is that if your function is less than some constant, that means that the integral of your function would be less than or equal to the double integral over the region of the constant function capital M, but we can slide that capital M outside, and if you integrate dA, you just get area, right? So this is just saying for all the region, add up the area in the region. That gives you the total area of the region, so that gives you M times the area of the region. So the upshot of all of this is that if your function is bounded above by some constant, your integral is bounded above by the constant times the area of the region. And of course the same thing goes on the other side. If your function is bounded below by some constant, then the integral of the function is bounded below by that constant times the area of the region.